The next speaker is Professor Yihong, who will give a plenary talk. And Professor Yihong is a professor at the University of New England, Australia. And he's a world-leading expert in reaction diffusion equations, particularly those related to population dynamics and other related problems. And he is a member of the Australian Research Council's College of Experts. And also he is a Web of Science highly cited researcher in 2018 and 2019 consecutively. So actually, it's better, Yihong, that you share your screen now.
Yep. Oh, ready? Okay, I'll do that.
So can you make it full screen?
Yeah.
Okay. So, okay, so the Professor Du's talk is on propagation, diffusion, and free boundaries. Professor Yihong, please start. Can you make it full screen? Can you make it full screen? No?
Yes, I can. Sometimes I make it a full screen and then something goes wrong. Let's have a try to see.
Okay. So if it goes wrong, you can.
Okay. It's okay from your side.
Yeah. I don't see.
Okay, so let's not make it full screen then.
Okay.
So, okay, go ahead, please.
Okay, thanks for Professor Matano for the introduction, and also want to thank the organizers for the invitation and for making this conference happen, even with this terrible pandemic of COVID-19. So today I just want to discuss some of these, I would say some aspect about this propagation, diffusion, and involving free boundaries. A rough plan of the talk is the following. So firstly, I'll recall some classical works and on reaction diffusion equations for trying to model the spreading, the propagation phenomena, including spreading of species, including spreading of diseases, for example. And then I'll focus on free boundary models, which are modifications of the classical models for these, for describing these propagation phenomena. So these will be in two kinds of free boundary models. One is with random diffusion, like in the classical works, and the other is with a non-local diffusion. And this is relatively new, and especially for models with free boundaries. So now let me start with the classical works. Let me mention Fisher's work. And he perhaps was one of the first to use the so-called traveling wave solutions to describe spreading or propagation phenomena. So Fisher, in this well-known 1937 paper, he used these reaction diffusion equation or parabolic equation, which is a semi-linear. So the right-hand side is just this very simple quadratic function of U. So A is a positive constant, which represents the net growth rate of the population. And there's another coefficient, which is also a positive constant, and that is the so-called diffusion rate. So here in this model, so U represent the population carrying certain good genes. So Fisher's purpose was to use these mathematical equation, this reaction diffusion equation, to describe the spreading of good genes in the species. So now he just pick up the population with these advantageous genes, and so this U is the population density of individuals carrying these gene at time t and spatial location x. So now here, so this consider very simple situation, x is in R1. And he observed that, so for any C constant greater than or equal to this particular C value, C0, which is obtained by using the parameter A and D here. So 2 square root AD. For any C greater than or equal to that C0, and you can find a special solution of 1, and which we nowadays call it traveling wave solutions. So he called a wave of a stationary form. So you look for a solution of 1 in that form with a capital V, a one variable function, but you composite the T and X in that way using a parameter C, unknown. And then you reduce this one, a PDE, into an ODE. And then he can show that for any C, the parameter C greater than or equal to the C0, and you can find such a solution. And this he calls the wave of stationary form. So now we call it traveling wave solution. So this kind of solution. And he claims that this C0, though with any C, so now this C is called the velocity of the traveling wave, or speed of the traveling wave. And he though we have a traveling wave for any C greater than or equal to C0, but he claims with some argument that, so these are minimal speed of a traveling wave. So this C0 should be the spreading speed of these population, individuals in a species with a good gene. In the same year, another independently, another classical work appeared. And these, nowadays, people call it the KPP result. So K for Kolmogorov, P for Petrovsky, and Piskunov. And they were motivated by the modeling of the same kind of a problem, that is to try to describe the spreading of genes in a population. And they proposed the same kind of equation, except now their F is more general. And now we call this kind of a F a KPP type nonlinearity. And that, of course, include this earlier one as a special case. And they proved a similar result. And for any C greater than or equal to this minimal C0, which is given by that formula. So if you take Fu to be this function, and the C0 reduced to the same number. So instead of A, now is a derivative of F at 0. For any C greater than or equal to the C0, you have a self-similar solution. Now we call a traveling wave solution. But for C less than C0, you don't have such a solution. And to demonstrate that this minimal speed C0 is special, and they choose a special initial function for this parabolic problem. And with this initial function, so this is 1 when x equal less than 0, and which is 0 when x is greater than or equal to 0. And they proved that the unique solution of 2 with this initial function converts to this traveling wave solution with a minimal speed. So W with the C equals C0 in that way. So here there's a high order term. So this gives you, if you forget about this high order term, this gives you exactly this traveling wave with a minimal speed c0. And this, of course, lent great support to the claim by Fisher that c0 should be the spreading speed. Now in 1951, another important paper appeared, that's by Scanlon. And he looked at one particular case and showed that in the real world, indeed, there's a constant spreading speed as predicted in these models. And the example is this famous muskrat spreading in Europe. So muskrat, these small animal, they are valued for their furs. So at the beginning of the last century, they were introduced from North America to Europe to be farmed for their fur. However, in 1905, and several escaped from the farm near Prague. And then in the next 50 years, they spread all over the European continent. And this is a diagram. We can say there are many closed curves here. Actually, so this is a follow-up of their spreading during more than 2 decades, from 1905 to 1927. And this is published in a paper in 1930. So each closed curve represents the spreading front in a particular year. So people followed that for over 20 years. And Scanlon was the first to try to use this diagram to establish something rather surprising by the way he did it. And what he did was that he estimated the area enclosed by a front curve. Well, this area, of course, changed with the time, and there are many years described here using these curves. And then he took the square root of this area and then checked how this value, square root of the area, changed with the time, t. And he found that this change is roughly linear. And now why he take the square root of at? Well, and if we, so suppose this shaded area is enclosed by this closed curve, that's the front of the spreading region in a certain year. And then if you use a circle to enclose the same area, and with the origin of this spreading. And then, of course, these R, the radius would change with the t, but then elementary mathematics tells us that, so this R of t, this R is proportional to square root of at. And so this factor is universal, square root of pi. But this R of t has a well-known meaning. It's called the range radius of these species. So therefore, Scanlon's observation says that the range radius of these muskrats increases linearly in time. So if it increases linearly in time, then the slope of this curve can be regarded as the average spreading speed. So therefore, that's how, so these average spreading speed, this constant spreading speed actually arises in the real world. And after this example, and people checked other examples where the spreading was recorded, and then there are many such examples following this rule. So this is the spreading of Japanese beetle in North America, and that's the data recorded, and then you do the same thing, you get this. So eventually you get this spreading curve growing linearly in time. And another example, and there are many more. So this is the house finch in North America, and that's how they spread, that's the record. and then you do a similar thing as Scanlon did, you get this linear spreading curve. And then I should mention this well-known work of Aronson-Weinberger in 1978. And in that work, and they looked at this more general situation, and they look at this Fisher equation. Well, not only this Fisher equation, look at this parabolic problem over Rn. They considered several kinds of nonlinearities. Now, just for convenience of comparison, I'll just choose the same one as the one used by Fisher. And then, of course, this problem would be well proposed if you supply with an initial function. Now, if you are interested in this spreading problem, so you choose an initial function to represent the population density, initially concentrated on a finite area of space. So we say in mathematics, we say it has a compact support. So U0 greater than 0 only on a bounded set of X in Rn. And of course, it's non-negative. And the support is not empty, otherwise U0 is identically 0. So for this special case, which is suited for describing the spreading of the species, and you have the following result. Now, first, let me explain how do we interpret this result. As we all know that, so because of the strong maximum principle, whenever, even if U0 has a compact support, once T is positive, so this solution U of this problem 3 would be positive everywhere. And in a sense, you might say, well, then so I can't find a spreading front because now you found the species everywhere. However, we can make a compromise that we nominate a small delta so that you regard this set, which depends on delta, and of course, this set of X, it depends on T. You regard this set as the population range of the species, and then it's easy to say this is always a finite set. And then, of course, then the boundary of this population range is this set U equals delta. And this can be used to represent the spreading front. And if you take this convention, and then the spreading can be, so this result of Aronson-Weinberger describes this spreading with a constant speed. So you look at the population density, you can show in this enlarging ball whose radius grows like C0t. Well, we have to subtract a small parameter epsilon here. Then inside of this ball, and the population is close to 1 for all large T. But outside of this ball, and here I have to add a small parameter epsilon, and then the population is close to 0. Now, this result clearly indicates that the front goes to infinity in all directions at this constant asymptotic speed, which is C0. So the radius increases with T. So the front is roughly in this spherical shell with the thickness 2 epsilon T. Compared to the radius C0t, this thickness is a high order. So therefore, the front spread, the radius increase linearly in T with a constant C0 here. So this C0 can be regarded as the spreading speed of this model. And this C0 actually is the same as the one discovered by Fisher and KPP. So if you take these Fisher nonlinearity, recover what is claimed by Fisher. So this C0 is just 2 squared AD. So this C0 is determined by this ODE problem. So now we call this traveling wave problem. And then, of course, you might wonder, so how so can we really use this formula to predict real spreading speed? So indeed, there are many works looking at these theoretical speed against observations. So so there are many situations, muskrat here and other species spreading. And so this is the A, and in the literature, in the biological literature, people use epsilon. So mathematicians are more careful, so we use A to just avoid confusion. So for these species, somehow you can estimate the number A, the net growth rate of the species, you get a range. So these, of course, biological problems are much more complex. You don't expect, like in physics, chemistry, for one material, the parameter you would get quite accurate parameter. Here, we only get a range. Similarly, for the diffusion rate, we get a range. And then you compare the theoretical prediction, C0, and the spreading speed and the observation, and you can say for the majority of these situations, the theoretical prediction gives you quite a reasonable estimate of the spreading speed. So now let me mention a bit more. And let's recall that at the beginning, I mentioned that the work of KPP, they even show, they showed that if you take this special initial function and the solution for large T looks like this traveling wave up to a high order term here. And actually there are work figuring out what is this high order term. And here is this. So actually this, you can figure it out in the radially symmetric case. That is, if your initial function is radially symmetric, and then you can show your solution stays radially symmetric in X for all time. And in that case, and you can approximate your solution indeed by this wave profile function Q with the minimal speed C0 in that way. So it's a C0T minus, basically that's X, and there's a constant C. But then, so this high order term of T actually is this one. You can figure this out. There's a log T here. And the coefficient is this one. So this capital D is the diffusion coefficient, and is the dimension. And then if we use the convention earlier, that is, we regard this omega delta t as the population range. Of course, this time, because the solution is radially symmetric, so this is a ball of a varying radius, say r delta t, at least for large t, it is a ball. And then we can have this a rather good approximation of this radius function, r delta t. So it is like a C0t, but with a correction term, this log t. Now that is for the radially symmetric case. If it's not a radially symmetric, and you can use a upper and lower solution argument, very simple argument to show then the population, the boundary of this conventional population range is containing this spherical shell of a finite thickness. And the radius of this spherical shell is largely C0t minus this correction term. In dimensions 1, this was first discovered, determined this correction term, log t correction term was first determined by Bramson. But he used a probabilistic method. And for in greater than or equal to 2, and that was the first discovered by Gartner, and a little later, and again by a probabilistic method. And here I just want to mention, and there are nowadays there are much more accurate estimate of this term, and there's a recent paper by Nolan and Rock Jeffrey and Ryjik, and they can even get these high order terms. And what's interesting is that this coefficient does not depend on the initial function, though this term, constant term, depends on the initial function. So now let me move to the topic about free boundary models. So as we mentioned earlier that, this model, the classical reaction diffusion model, we call it the Cauchy problem because it's an initial value problem. And we have to make this convention in order to describe this spreading speed C0 clearly. And in some situations, people care very much about exactly where is this spreading front. And then, of course, this one, in this convention, it depends on the choice of delta. So this C0, of course, does not depend on the choice of delta. However, if you care very much about the spreading front, then you don't know what is the right value of delta to choose. And then, so in this free boundary problem, and we try to model the problem with this precise front appearing in the model. But then, of course, the problem becomes more complicated. So now, we use omega t, a varying domain, to represent the population range at any future time t greater than 0, and where we still use the same reaction diffusion equation to describe the population growth. And then the problem becomes a so-called free boundary problem, because we don't know how this omega t changes. So now inside omega of t, we have this same equation, and at the boundary, the population density is 0. We also have this initial function. So now, because omega of t changes with t, we have to determine in the model how this changes. So this equation basically is the one, together with the u equals 0 here, that governs the evolution of the change of the boundary of this varying domain. And this condition is borrowed from the Stefan condition in the one-phase Stefan problem. So here now, in this model, we modify the classical one in order to describe the front explicitly in the model. And the price we pay is that we reduce the classical Cauchy problem into a free boundary problem. So when f is identically 0, and actually this reduces to the well-known one-phase Stefan problem model, and that describes the melting of ice. And that has been considered by many, many people since the 1960s. And of course, for this kind of a problem, to handle the free boundary, its regularity is very difficult. And so here, what's the physical meaning of the free boundary condition? And that equation basically says if this is smooth at the free boundary, then any point on the free boundary would move in the direction of the orthonormal at this boundary of omega t. And with the velocity proportional to the spatial gradient of the solution at that point. So the proportional coefficient is mu. Now, if we are in a simpler situation, say if the solution is a radially symmetric or spherical symmetric, and then the free boundary would become the sphere, and then that can be represented in that way. So the derivative of the radius of the changing sphere is proportional to this gradient. The gradient now is the partial derivative of u with respect to the radius variable r, evaluated at the free boundary as ht, when r equals ht. So this mu is just this positive constant here. So now we borrow this Stefan condition for use in the spreading problem. Then what's the meaning of this mu? So in this paper, joint paper with the Bunting and Krakowski, and we made an assumption that so k units of the species is lost per unit of volume at the front. And then we can deduce that mu equals 1 over k. Well, this is based on an assumption. And unfortunately, in ecological problems like the one we want to model, and we don't have proven principles to use. So this is based on just one assumption, and a reasonable assumption. Another point I want to make is that, so for this problem, so even if omega 0, the initial omega 0 has a smooth boundary, and this initial population, initial function u0 is smooth, and there's no guarantee you indeed can have a classical solution that is a solution satisfying all these in the classical sense. So, however, we can show we always have a weak solution, a unique weak solution defined for all t. And in such a case, and the omega t is always regarded as the region of X where the weak solution is positive. So it changes with the t. However, in general, the smoothness of this boundary is not guaranteed. So our basic result for this problem, this free boundary problem 6, is the following. So this is a result from a joint work with Professor Hiroshi Matano and Professor Clay Wang, who is now working at Wuhan University in China. So we can show that, so for this population range determined through this weak solution in that way, and we can show this population range increases with the time all the time. And also is a boundary, is smooth outside the convex hull of the initial domain omega 0. And furthermore, we have a spreading vanishing dichotomy in the following sense. So we look at the limit of the population range when t goes to infinity in set language, and this is defined in that way because it's expanding in time. So that's the limit, omega infinity. And then we can show in the limit, we only have two possibilities. Either this is a bounded set, or this is the entire space. So this cannot grow into a general unbounded set in Rn. So either bounded or entire space. And in case A, when it's bounded, so omega t, the population range has a bounded limit, and then the population density has to go to 0 uniformly. That's why we call it the vanishing case. So the species vanishes eventually. And in case B, we call it the spreading case. And we can show, so now I have to mention that for simplicity, so we assume that F is taking this special nonlinearity, the Fisher nonlinearity. So the result holds for a more general nonlinearities, but for simplicity and for easy comparison with the classical result, we focus on this particular nonlinear, the Fisher KPP nonlinear. And then in that case, so when spreading happens, that is when the population range has limited the entire Rn, and the population density goes to 1. Locally uniformly in X, not only pointwise. Furthermore, in that case, we can come back to say more about this free boundary gamma of T. So we can show for all large T, this gamma T becomes a smooth closed Haber surface contained in a spherical shell. The spherical shell has an inner radius R of T, and the outer radius is R of T plus a constant. This is bounded by the diameter of the original omega 0. And this radius R of T goes to infinity linearly, roughly linearly in time, but this constant, so I'll explain it in a moment. This is C0 star, is a positive constant. So let me also comment on this. So why this? We can only prove smoothness outside of the convex hull of omega 0. Indeed, we cannot remove this. So indeed, we can construct omega 0. So like you consider omega 0 as a spherical shell, and then you drill a hole. So spherical shell take minus a small hole, and you can make this boundary of omega 0 smooth, and then you can say singularities can appear inside of the convex hull of omega 0. However, and when this omega T would grow to entire Rn, and these bad things would disappear after some finite time. And then after that, all these bad things disappear. So the boundary of omega T would be outside this convex hull of omega 0, and then it's a smooth, is a smooth closed surface, and is contained in a spherical shell. And now this C0 star, and it's like in the classical case, it's determined by looking at a traveling wave type solution. And here, because we have a free boundary problem, and the ODE becomes 1, not over the entire real line, but in the half line. For that reason, we call this a semi-wave. And this C0 star is just the unique speed. So here is not a minimal speed, but it's a unique speed. So here also, not only this, so this equation and the value of u at 0, the boundary, and at infinity, the other boundary, we also need this equation. So that determines a unique C value, C0. And this equation arises from the Stefan condition in the original problem. And this is contained in a paper joined with Bendong Lo of Shanghai Normal University. I should mention that actually this spreading vanishing dichotomy was first observed for the simpler case, space dimension equals 1, in the joint work with Zhigui Lin of Yangzhou University in China. And of course, so we started with the space dimension 1 for these kind of models, because in space dimension 1, we don't have the trouble about technical difficulty about the regularity of the free boundary. In space dimension 1, the free boundary consists of just 2 points. So omega T becomes an interval. And then we can focus on the long-term dynamical behavior. But in high dimension, this becomes a much more challenging mathematical problem. And in order to fully understand the long-term dynamical behavior, we really cannot avoid to know some of the regularity of the free boundary. And fortunately, in this case, we indeed can have a quite a good understanding of this regularity and the long-term dynamical behavior. So here, this just shows, so this is the classical problem, and then the traveling wave solution with the minimal speed, you know, a self-similar solution for the equation. This way, it's traveling wave described the spreading of the species. And for this free boundary problem, we get this so-called semi-wave that has speed C0 star, and this is how it looks like. And here, the front, well, we have to nominate a delta to cut these to get a front, finite front. And this one, because the variation in the model, the front is given precisely at any future time. And also we can see more about how, so here, let's recall, this tells us that, so in the front is roughly, it goes to infinity roughly like this linear function, C0 star times t. We can see more by using this semi-wave. So this is a result from joint work with Hiroshi Masuzawa and with Maolin Zhou. And in that paper, we considered the radially symmetric case, which is more easy to handle. And then, so basically you assume your initial domain omega 0 is radially symmetric and U0 is radially symmetric. And then, so the weaker solution would be radially symmetric all the time. And actually in that case, you can show is actually, if U0 is reasonably smooth, and you know this is a classical solution. And then omega t would be this ball with a changing radius. So we call it R of t. In that case, we can show actually the solution U, radially symmetric, its profile looks like, it's described the profile of the semi-wave solution. And this solution with a C equals C0 star. So this determined by this ODE. And now, of course, inside it, and so you use RT minus X naught. And this RT and can be expanded in that way. So the highest order term is a C0 star T. Then there's a correction term, also involving log T. And we can determine the coefficients. So this n is the dimension, and this C1 star is a constant independent of dimension and independent of the initial function. And then this difference has a limit, which converts to a constant. This constant is dependent on the initial function U0. So this C1 star is determined in this complicated way. Now, this radial result has implications for the general non-radial case. And again, you can use a comparison argument to show in the non-radial case, and this free boundary for large T is contained in this spherical shell with a finite thickness. And the radius of the shell is roughly C star T minus this times log T. That's the correction term. And finally, we can also say something about the relationship between the modified model with the free boundary and the classical one, the Cauchy problem 3. And so we can say the relationship clearly when we let mu go to infinity. So this is a result from my joint work with Zhongming Guo of Henan Normal University. So now, of course, this solution of 6, because it's a free boundary problem, the solution involves the density function U and the population range omega of T. So 2 unknowns in 6. And if we fix T or fix T in a bounded interval away from 0. And we can show that when mu goes to infinity, so the population range would go to Rn, and the solution U, depending on mu of 6, would go to capital U. What is capital U? Capital U is the unique solution of the classical Cauchy problem with the same initial function. So this really says that, so 3 is the limiting problem of 6 when we let mu go to infinity. And if we look at the spreading speed, so here so in the free boundary model, the spreading speed, so from this result is C0 star. Of course, these C0 star also depend on mu. And in this work with Bendon Low, we proved that. So this depends on mu and it's increasing in mu and it's also continuous. And when mu goes to infinity, these C0 star would convert to these C0, the spreading speed determined by 3. So all this really indicate that 3 is the limiting problem of 6 when we let mu go to infinity. So now let's go back to say what is mu. So mu is this parameter here, and our assumption is to say, so mu go to infinity really implies k goes to 0. If you assume that you don't have a population loss near the front, and then you go to the case mu converts to infinity, and that reduces the problem to the classical Cauchy problem. So now there's a comparison so between the classical and the modified free boundary problem. So they share several important properties. The first one is the shape of the front. They are both approximated by spheres. And also they both predict spreading speed. So the classical one, the spreading speed is C0, and the modified one, C0 star. And of course, there are essential differences between the two. And the first one is about the location of front. And 6 gives us, in the model itself, gives us the precise location. That's the free boundary. And 3 does not provide such a precise location for the front. And the other difference, important difference, is on the success of spreading. So 3 guarantees consistent success of spreading, because as long as your initial function is not identically 0, then the population density would convert to 1 when time goes to infinity. But for 6, there are 2 possibilities. You can still have a vanishing. So these population range convert to a finite region, and then population density goes to 0. And can we guarantee this happens? Well, there are. It's very easy to find sufficient conditions. Actually, in this joint paper with the Bendon Low and Maulin Zhou, and we can use this initial function, parameterize it like this. You fix a phi and multiply it by a parameter sigma. Yeah, you can show you can get a critical sigma star, so that sigma greater than or equal to star is exactly when spreading happens, and when sigma is less than sigma star, then vanishing can happen. So indeed, both can happen. And the final difference actually is you look very carefully about this correction term. And in the classical model, there's a Bremsen correction term, log t term. Actually, if you look very carefully at the coefficient, you find that the dimension appears here. So n plus 2, that means even dimension is 1, you have these correction terms. However, in the free boundary problem, and then there's a factor n minus 1. So therefore, in space dimension 1, so the modified model 6 doesn't have these a shifting term. Okay, now let me move to this non-local diffusion case. So this is so especially for free boundary model, this is much more recent. I'll just report some recent works I obtained with my collaborators. But let me also start with some background. So let me mention that, so today I'm just focusing on one rather narrow aspect about this modeling of a propagation, and there are many important developments. I don't have time to mention, and also I'm not the right person to report them. So so these 3, and also for these 6 free boundary model with random diffusion, there are lots of successful extensions of these basic classical models to more realistic situations, including extensions to systems of equations. And also a very important aspect of this is to various heterogeneous environments. But now today, let me focus on this diffusion. So these 3 and 6, we both used these Laplacian U to model the spatial dispersal of the population. So this is also called a random diffusion, or sometimes called a local diffusion, to contrast with what I'll explain, the non-local diffusion. So why the need to consider non-local diffusion? Well, there are many phenomena. So these random diffusion models cannot capture. So one is the so-called acceleration of spreading. And this has been observed in many situations. And one main cause, or one of the main cause, is the long-range dispersal. So long-range dispersal, like spreading of disease, and so people or animals carrying disease can be carried by modern traffic tools, like a train, like a car, like an airplane, to long distances. And even in the natural world, and if we consider spreading of plants, and the seeds of a plant can be carried far away during a storm, for example. So this kind of spreading cannot be captured by random diffusion, like these kind of operators. So then non-local diffusion can cooperate these kind of factors, like long-range dispersal. So now let me explain very briefly what's the difference between local or random diffusion and non-local diffusion. So let's look at the one space dimension case. So now the space is R, and we divide it into, so we look at the modeling process, and we look at how to go from a discretized situation into a continuous situation. So then that's the model, classical model in one space dimension. Let's see how did we arrive at that. So if we divide the space into small intervals, or called blocks of equal length delta x, and just discretize time into steps of delta t, length delta t. So a random walk, random diffusion is derived from this random walk assumption, that is, from time t to the next time step, each individual moves from its current location either to its left neighboring block or neighboring interval, or to the right neighboring interval. So it cannot, but with a probability half, it cannot stay still. It has to move, but it can only move to the neighboring block, either the left or the right. And then by using a limiting process suitably, you would get this diffusion term in the classical model. So now what's the non-local diffusion model? Well, the non-local diffusion model, one of these commonly used non-local diffusion model looks like that. How did we arrive at that? Now, the assumption in this discretized situation is that. So now an individual at a time t, then from time t to the next time step, so these can jump from the current location, say x, to any other location, y, but with a probability function. So this, in the general case, this is a two-variable function. But here we just concentrate on this simpler situation. So this probability is only dependent on the distance between x and y. So in one space dimension, is this one. And in that case, so you take the similar limiting process, instead of this d uxx, you would have this term. So there's a difference. So this basically tells you, you look at location x, then this integral, the kernel function, and you forget about this term, dy, tells you the population that moved from a location y to x. And this integral minus that times that, this tells you the population that moved from x to other places, all the other locations. And therefore, that's the quantity of the change of population at the location x from t to the next time step. So therefore, so replacing these, we should use this integral operator. And this kernel function j, so in the case I described, usually we assume it to be a continuous function, non-negative, and even, and jumping from x to place on the left and to place on the right, they have the same probability. And it's normalized, so integral is 1. And then people notice that one important condition to classify the kernel function is the so-called thin-tailed kernel. So it's described by this in this way. If for some positive constant lambda, this integral is finite. Because it's even, we only check the integration from 0 to positive infinity. So if this is a finite, we would say this kernel function is a thin-tailed. Otherwise, we would say it's a fat-tailed. So now if we compare, so now we have this 9, and we want to compare with this classical one, say this in one space dimension. And of course, generally, we don't have to restrict to one space dimension. Now for simplicity, let's just concentrate on that special situation. So it's known that if J is a thin-tailed, many results obtained for 3, the random diffusion model, and can be proved for this non-local diffusion correspondent, like finite spreading speed and so on. However, if it's a fat-tailed, then there's something new, essentially new. That is, so accelerated spreading happens. So from a well-known result by Weinberger in 1982, this is a rather deep paper, but a theoretical paper. So you use the theoretical result, apply that to 9, then you can show well, let me also explain. So non, of course, now we assume we use the Fisher nonlinearity. So this non also has these property like these classical problem 3, and the solution with this U0 non-negative with the non-empty compact support would convert to 1 locally uniform as t goes to infinity. And also for any t positive, the solution would be positive for every x. And then similarly, you nominate a delta, you look at the population range in defining that way, and you look at it as a free boundary, sorry, not free, it's a boundary to represent the front. And then you want to know how does the front move? And in one space dimension, this is a setting R, R1, and you look at its supremum of this, the infimum, and you can show, you look at these, and you can show that if J is a thin-tailed, then this limit converts to a unique positive constant, say lower star. But if it's fat-tailed, this limit is no longer finite, it's infinity. So that's new. So this thin-tailed case is like this classical case of a 3. Actually, these C star is also determined by the corresponding minimal wave speed of traveling waves for the non-local case arising from non. And moreover, if you look at a special kind of kernel functions, so if Jx is like this x to the minus sigma, sigma greater than 2, in order for the integration to be finite. And then you can say, so these functions behave like this exponential function for some alpha positive. So this is from a result by Garnier, a French mathematician. And if J is like that, because beta is greater than 1, and you can check easily, this kind of a J still is not a thin-tailed, it's a fat-tailed. And then these functions, or the spreading would be again superlinear, but it's like a power of t. Sorry? It's like a power of t. And also another kind of non-local diffusion is obtained by looking at the fractional Laplacian. And for this kind of fraction, well, you find this kernel function actually is a singular, not continuous, not bounded. And indeed, this is not integrable. But still, you can use these to form this convolution operator, and you can understand this as is a principal value and obtaining this way. And if you replace in the classical model 3, the minus Laplacian U by this fractional Laplacian operator S between 0 and 1, and then this result by Cabrera and Jack-Hoffrey, they showed again you have exponential spreading. So this spreading is like a to the sigma star t. Sigma star is calculated this way. This is in general n dimension. Now, what's the free boundary problem with a non-local diffusion? Again, we look at this one-dimensional case. This is a simplest case. Indeed, so far we only look at this one space dimensional case. And so, of course, we replace the diffusion operator by this one, and also now it's more natural to replace in the free boundary condition. So now this is an interval. We have a right end, left end of the free boundary, and it's better to replace. So in the random diffusion case, here is mu times u partial derivative with respect to x, evaluated at x equals ht. So now it's better to use this. And to obtain this kind of equation, we actually use a similar kind of biological assumption that we can arrive at this. So we assume now for the initial function, we assume it's a continuous positive inside of the initial interval and 0 at the boundary. And for the kernel function, we make this general assumption, continuous, non-negative, and even, and at 0 positive, normalized, and we also assume it's bounded at infinity. And as before, let me explain for this special Fisher nonlinearity. Okay, I think I'm a bit too slow. I'll just skip this part about this meaning of the free boundary conditions. Let me mention that, so for problem 10, so this one that was proposed independently in these two work. So this is my joint work with Jiafeng Cao from Lanzhou, Fang Li from Guangzhou, Sun Yat-sen University, or Zhengshan University. These are Wan Tong Li of Lanzhou University. And also this group, also their paper appeared in 2019. So they, in reference to, they consider the case F is identical to 0. So in this paper, we consider the case Fu behaves like that one. But the free boundary conditions are proposed independent and they are exactly the same. And what we obtained in this paper, so we proved that for problem 10, the nonlocal diffusion free boundary problem, we have existence, uniqueness defined all the time, and here is a classical solution. And we also have this spread and vanishing dichotomy, and that's a parallel to the random diffusion case. And we can also determine exactly when spreading happens, when vanishing happens. So these, of course, if you look at these criteria carefully, you would observe some differences from the local diffusion model with the free boundary. But of course, here, let me focus more on the spreading speed. For the spreading speed, and this is based on a preprint joint work with Fang Li of Guangzhou and Mao Linzhou again. So we proved that, so for this non-local diffusion model, and this condition on the kernel function is critical. So we call it J1, that's x times Jx is integrable. So if J1 is satisfied, and if a spreading happens to the solution for U, and then there's a linear spread. So we have, again, a finite speed. Of course, this C0 is different from the C0 I mentioned earlier. And if J1 does not hold, then we have accelerated spreading. The limit is infinity. And how to determine this C0? And again, we look at semi-waves. So this now for the non-local model, the semi-wave consists of these equation, like a semi-wave equation. You look for self-similar solution, you get this one. Now you have this C unknown. And these are conditions at 0 and minus infinity for phi. And this is another condition arising from the free boundary condition.
Yihong, you have 1 minute left.
Yes, I'll just have just 2 more slide. And so we proved that, so for this problem has a unique solution if and only if J1 holds. So now the last bit is about the spreading speed. And we can see more about the spreading speed if we restrict this kernel function. So we look at this kernel function behaving like x to the minus alpha. And in that case, the basic assumption J is equivalent to say alpha greater than 1, and J1 is equivalent to say alpha greater than 2. And in that case, and we can see more. If alpha greater than 3, and we can show this C0t minus ht, the difference is bounded. But if alpha equals 3, this difference is of order log t. If alpha is between 3 and 2, this is that. So this is the case where J1 holds. If J1 does not hold, that is alpha is between 1 and 2. If alpha equals 2, then this does not behave like linear, it's like t log t. And if this is between 2 and 1, it's this one, greater than t to the 1, but faster than t, but it's like this. I think I'll stop here. Thank you.